So just make sure you know. Okay, we can hand it over to Gavin, who is online, to give an introduction for our speaker today.
Thank you very much, Maggie, and thank you everybody for turning up today. This is quite an exceptional moment. Vittorio has been at Giss since 1968, a time at which I was 6 months old. So my entire life, effectively, Vittorio has been here, and you know, you might think, for instance, that the Giss building only has 7 stories. It has a lot more stories, and we can connect with the folks that have been here decades to really, get a sense of how those stories weave together. Lots of things have happened here that often people are, ignorant of, or never looked into. But there are really strong threads that take the work that we're doing here today, right now, back to some of the most important and relevant physics and astronomy and earth science conversations of the last of the last half century. Just to give you a sense of how long this is, right? In 1968, right, the First World War was as far in the past as 1968 is today, right? And we have people that span almost that entire time. It's really very impressive, the dedication shown to the institution, to NASA, to the people that we have here at Giss is truly exceptional. And I'm greatly looking forward to hearing more of Vittorio's adventures. Some of which I have heard, but I'm sure there are many that I have not heard. And I look forward to everybody else engaging with this fount of knowledge. And so, with no further ado, Vittorio, take it away.
Okay.
Maybe one last little bit of opera Italian for you. Vincero. You can do it. Thank you very much.
Careo? Thank you, Gavin. I remember that when you Gavin, became director of Giss, you made a small speech down on the 3rd floor. If you remember, you said that you visited Giss and you had a long conversation with David Rind, and after that conversation, you decided to be part of Giss. I remember that statement because something like that happened to me too in 1968, except that I was not here present, and the equivalent of Rind was a Chinese astrophysicist who I hope is connecting with us, Dr. Onggi Chu, who was very famous in astrophysics because, among other things, because he invented the word quasars, which now everybody, from which then there was the word pulsars, etc. So he's an extremely rich and ingenious man, without whose confidence, and I would not be at Giss. So he could not make it. He's retired now. He's very active. He's just written a book on the history of China, and he could not make it to New York, but I'm sure he's listening, and I would like to thank him 55 years later for the confidence that he gave to me, even though he had no reason to. I remember I met him at the University of Mexico Department of Astronomy after one talk that he gave, and he asked me after the talk if I knew quantum electrodynamics, which is the science that put electromagnetic field and atoms together. And I replied the truth. I said, I'm teaching a course on it. So I don't have working experience because I haven't finished my course, but at least I know what the whole subject is all about. And he told me that's all I need because the topic that I would like you to work on has to do with that. The topic was, how does a gas of electron behave in a magnetic field? And that was the topic he wanted me to work on. That was the topic that he gave me when I came to GISS in '68, and that's the first paper that I wrote with him. Here is 50 plus years of GISS, and the second one is a postcard that my wife sent me, saying that, Mark Twain said that, so you can read it. Age is an issue of mind over matter. If you don't mind, it doesn't matter. Which, and then after that, she gave me another birthday card from Pablo Picasso that says, I don't have it here, but he said it takes a long time to become young. And those are the topics that I've been working on since I was here at GISS, January 1968. Now you don't remember because you were not even born, but 1968 was a very tough year. The Vietnam War was raging. Lyndon B. Johnson was in the White House without knowing what to do with that war. There was continuous demonstration against the war from the students coming in on Broadway. They even, at one point, there was a rumor that they said they would blow up the computer at the NYU Mathematics Center because they were working for the Pentagon. I don't know if that was true or not, but it was very tense. The situation was very tense. All over Europe, in '68 was the revolution. There was upheaval in every possible campus in Europe. And so when I came here to New York, we were on my second visit, but the first one is only as a tour. So I was scared to death of the city that was so tough. And I'll tell you the details in a little while. So since I've been there, I'm working on different fields because I work later on, I will tell you, I work with a scientist by the name of Dirac, one of the fathers of quantum mechanics, who told me that if you don't enjoy what you're doing, you might as well go to Wall Street and become a millionaire, which is very true. He tried to go to Wall Street, and he came back because he loved his job more than Wall Street. So it is true that I work in different fields because also the atmosphere in which we're living was producing this field. That was the field in which I worked. So I work in high magnetic field with my first topic, high density matter, which I'll tell you all about, cosmology, and turbulence. Turbulence has been the last love of my life, and I will tell you something about that. And we go to the next one. So why did Donggi Chu wanted to go to study matter in a strong magnetic field? Well, because it was in the air. And I remember the pulsars in neutron star had not been discovered yet. So it was all speculation, but Donggi Chu was a very imaginative person. And he said, if you take a star, sooner or later the star will die, will collapse. So in the collapse, the magnetic field, the flux is conserved. So the flux B times the radius is the same. So if you take the star like the sun, which is 10 to the 10 centimeter, if you squeeze it down to the size of Manhattan, a few kilometers, the ratio is 10 to the 5 or 6, the square is 10 to the 12. So whichever magnetic field you have at the very beginning is boosted up to 10 to the 12. There was no idea what collapse of star was, but they were in the air. People think that would be. So it makes perfect sense for him to ask me to walk into the magnetic field. Let's wait for Michael to find his phone. And the magnetic field, the strength of magnetic field we were working on was 10 to the 13 Gauss, which is orders of magnitude more than any magnetic field you have on Earth. So the matter in those fields must behave very, very, very strange. And it didn't. The energy if you take an electron, if you put it in a magnetic field, you know from quantum mechanics that so the motion along the magnetic field is free because there's no force. perpendicular, the magnetic field is quantized like it was in small or Larmor radius. So that's why you have an energy which is free, the energy. Pz is the momentum in the z direction, which is the same as in, but in the other direction it's quantized, and is the quantization number, which is 1, 2, 3. So it's a funny situation of a free particle in this direction and very circumscribed particle in the xy direction. So we wanted to know the next one, the magnetic field. So only Chu and I didn't know how to do it. So we went to Yeshiva University Department of Physics because Freeman Dyson was there. And Freeman Dyson was one, he just died a few years back, one of the most knowledgeable person in physics. So we consulted with him. He took us to lunch and we had a very good conversation. At the end, he says, I cannot suggest any way of doing the program. So we came home a little bit sad, but on the other hand, if Dyson doesn't know how to do it, I shouldn't feel all that bad that I cannot do it. Then, without telling Dr. Joy, went to Rockefeller University because that was George Uhlenbeck, one of the father of statistical mechanics. If he doesn't know how to do it, forget it. So, my appointment was for 6 months, by the way. So I had to do it before June. So I talked to Uhlenbeck and he said, no, I don't know how to do it. It's a beautiful problem, I don't know how to do it. That was it. Then the last resort, it was the smart thing to do. I went to Colombia just to talk to Rabbi. Rabbi Isidor Rabbi was the Nobel Prize at Colombia, one of the most, the smartest people I ever met in my life, one of the nicest people I ever met. I remember once it was at our place for dinner and look at our son, who was very, very small. He said, Vittorio, that's the best paper you ever published in your life. So I said, Rabbi, help me out. He said, yes, I can help you out. When I was a postdoc in Germany, Heisenberg asked me to solve the magnetic field, the equation in a magnetic field. So Dirac is the relativistic equation because the density is so high that the electron is relativistic. So I have the equation for one electron in a magnetic field that can help you. I said, well, it's better than nothing, better than what I got for other people. So that was it. I had this wave function. I didn't know what to do with it. How do I compute the entire? So then April 4th came. So I spent January, February, and March with no result. My appointment would last until June, after which I would return back home very happy to having spent 6 months in New York without result. But it wasn't the first time because I was told that the same problem was given to another postdoc here, and he also did not have much success, so I didn't feel all that bad. Anyway, April 4th, Thursday, April 4, 1968. We were downstairs on the 3rd floor having coffee. At that time, we had coffee every day. And the news came they had killed Martin Luther King. Martin Luther King had been assassinated in Memphis, Tennessee. And of course, the whole country was in turmoil, especially in New York. So Harlem was going to flame. Fortunately, we had a very good mayor, Felicity, who that evening, without bodyguard, without police, nothing, he went to Harlem and walked up and down 125th Street. And the temperature went down and it quieted down everybody. There was no riot in there. But at 3, that happened 3:15, at 4 o'clock in the morning, the FBI came here and closed Giss. They closed it down and said, go home. And come back Monday or Tuesday because we don't. There was a NASA sign outside that was taken off, just in order to invite people to be dangerous. So I went home, which was not home. It was an hotel in 103rd Street in Riverside, and I stayed there for 3 days because I didn't know very well New York. So I decided to buy all sorts of supplies, and I had a small kitchenette, and I cooked for myself. Now, being the horrible cook that I am, on Saturday night I cooked up something. I forget what it was, but it was so terrible that during the night I had nightmares and until I realized how to do the problem. It just occurred to me that in quantum electrodynamics there is a quantity called the energy momentum tensor, T mu nu, which needs the wave function psi that I have from Albert. I could put them together, extend one field to one wave function to a field, compute the component of that, and have the result. Well, I spent Sunday, Monday, and Tuesday doing nothing else with algebra, and at the end I came in on Tuesday or Wednesday, as it was, I don't remember now, with the equation of state that I was expected to come up with. And in the next slide, I show the result. As you can see, there's too busy, unfortunately, but just look at the pressure, the one that says PZ and PXY. PXY is the pressure, which is not in the XY direction, which is much smaller than the other, because the electrons are all stuck into small orbits, so they cannot exert much pressure, whereas in the Z direction, they can have as much pressure. So it was very anisotropic result, which is what I expected. After all, it was no surprise. One of the reasons why I didn't realize at the very beginning was my fault, because I keep on talking about pressure. Now, pressure is a scalar. If you look at any book in statistical mechanics, the pressure is one pressure, it's a scalar. But here we needed the tensor. So I shouldn't have called it the pressure, I should have called it an energy momentum tensor. So perhaps the people I thought were misled when I used them. I wanted to have a non-isotropic pressure. It seems to be a contradiction in terms. But anyway, we got this equation. It was an exact equation. Now, you know of one equation which is exact equation of state, and that is the equation of state. Come on, Vivian, sit here. Equation of state for a perfect gas. That's an exact equation of state, right? So why do we call this a perfect gas? In spite of having Coulomb interaction among the electrons. The electrons are not interacting to the Coulomb forces. So how could it be a perfect gas equation of state? It is because if you look at the interaction between two electrons, the Coulomb interaction was like 1/r, which is the density to the power 1/3. But the kinetic energy goes like p squared, and for Heisenberg principle, p squared is 1/1 length squared. A length square is density to 2/3. So as you increase the density, the kinetic energy goes faster than the potential energy, and then the gas becomes freer and freer in that sense. So that's why we can call it a perfect equation of state, because the Coulomb interaction is overpowered by the kinetic energy interaction. So I think that is the only second example that I know of exact equation of state. Of course, Dr. Chu was ecstatic, everybody was happy, and I kind of saved my job in the sense that they told me, but that's too early you have until June. I said, well, until June is top line, but I can do it before, right? So I did it. But to tell you how difficult was 1968, after Martin Luther King, in June, Robert Kennedy was assassinated in the hotel in San Francisco, I think it was. In August, the Russians decided to give freedom to the Czech. They invaded Czechoslovakia. That was another tough year. So it was and in the meanwhile, Lyndon B. Johnson said publicly that he would not seek a re-election, he would not become president again, and that gave room to Reagan to become president. So it was a year that history-wise, politics-wise, science-wise and it was the year in which they discovered pulsars. Little detail. Right? In January, I have here the exact reference because I'm not very good at remembering. But in January of 1968, Anthony Lewis from Cambridge, England, wrote a paper in Nature saying that they had discovered some very strange, from the radio telescope in Cavendish, in Cambridge, there's some very strange output that they called the little green man. They didn't know what they were, so they called the little green man. So then it turned out that Tommy Gold, who was an Austrian scientist in Cornell, identified that with neutron stars. So neutron stars had finally been discovered. They've been in the literature since 1937, when Robert Oppenheimer, the father of the atomic bomb at Los Alamos, had written a very classical paper on the size of neutron stars. And we all knew, everybody knew that there was of the order of 10 to the 10, no, 10 kilometers, 10, 15 kilometers, size of Manhattan. And so that was a confirmation of that. But we didn't give up on that. We can have the next one. Ongi and I were very excited about this magnetic field stuff. So we asked my wife, who's here to defend herself, to study the neutron beta decay. A neutron is an unstable particle. It lives about 15 minutes. Then it decays into a proton, an electron, and a neutrino. And it's a very famous decay because that's how the neutrino was invented. Because Pauli, Wolfgang Pauli, the famous Swiss scientist, tried to conserve energy and momentum with that neutron decaying to a proton and electron, he couldn't do it. So he had to include another particle to save conservation. And he wrote in his memoir that that day he made the worst, I'm trying to remember, the worst mistake that a theoretical physicist could make, invent a new particle in order to save. And the new particle is in a neutrino, which has been ever since the talk of the town. I mean, everybody talks about neutrino as a mass, doesn't have a mass, etc., etc., etc. So he invented a particle out of the need to conserve energy and momentum, and it turns out to be very successful. Rather than being sorry, he should have been, I'm sure he was very happy with that. So one possibility was the neutron beta decay, because if you have a neutron, it decays into the proton, and then there's an electron. If an electron comes out and finds himself embedded in a magnetic field, then what happens? Now, the proton is also charged, but the proton is so heavy that the magnetic field, in order to affect the magnetic field, you need a magnetic field of 10 to the 19 Gauss. So magnetic field, the proton doesn't care, but the electron does. The electron does, and therefore it was made perfect sense to compute the lifetime of a neutron. Will the neutron lifetime be smaller or larger than without magnetic field? And the simple argument showed it must be shorter, because you have a perfectly well-developed formula to compute the transition of an electron. You use the V minus A, the vector minus actual interaction or weak interaction. The wave function are the one that was given to me by Ravi, so we had all that. You can put them together. And of course, as Fermi once said, all the matrix elements are essentially unity. So that was not the problem. The problem was the density of final state, because when you have a reaction like that, what really decide the lifetime is the density of final state, which is a statistical property that depends on the environment. And that is the one that is much larger than in the case without magnetic field. And that's why the result, here it is. See, the neutron was into the proton plus an electron plus a neutrino. I went back and looked at the paper of my wife, which was published. Oh, I have a funny story about that, which was published in 1969, and it's a tour de force. I mean, it's really amazing what, not because she's here, but it was very, but I tell you, so that was 69. Now, that was submitted, let me see, it's an interesting story, I think, was submitted April 1st, 1969, was accepted December 10, 69. In the middle of that, we had our son, our only son. August 8th, he was born. And I remember that we were expecting our son, we were very happy, etc. And then when my wife finally was free from her duty as a mother, and I asked her how she was feeling, she said, "Did it accept it?" And I said, "Is my son or was it eight cannot be my son. It doesn't say accept him." He was referring to the field, if her paper had been accepted. So that's the deformation of giving out birth to one. So I hope our son is listening to everybody here. He was sighted for the first time at the Mount Sinai Hospital where he was born. So then the paper was accepted. It's published. Here it is. Now, so the neutron, you can see the neutron lifetime goes down. Instead of being, this is the lifetime divided by the lifetime without magnetic field, and it becomes 0.54 thereabout for the magnetic field. So it's reduced by a factor of 2, which is considerable. This also is an exact result because everything was computed. Okay, next one. Oh, then we went to the hydrogen atom. We were very, yeah, okay, I don't know. Anyway, we wanted to study more magnetic field stuff. So we thought about the hydrogen atom. Hydrogen is the simplest possible atom. It's one proton and one electron going around. That's it. It's quantum mechanics 101. The binding energy is 13.6 electron volt. Everybody knows that. The question is, if you put a hydrogen atom in the magnetic field, will the binding energy go up or will the energy go down or will it not go anywhere? It will stay the same. Well, a simple qualitative argument was that it will go up. Simply because if you have one proton, which is here, and you have one electron, if this electron goes around in a three-dimensional environment, every once in a while it goes next to the proton, but not all the time. But if you have one dimension, then the poor electron has to go to the proton all the time. So it feels the interaction much more frequently, and therefore its binding energy must go up. Now, does it go up from 13 to 20, 50, 60? Well, we derived 180. And Mel Ruderman at Columbia did the same computation with variational method. He got the same result, more or less. So it's 180. So it's very tightly bound. Forget about ionizing that atom with 180 electron volt. The electron is really slave of that proton by 180 electron volt. That was a very nice result. We couldn't do it analytically because the Coulomb interaction is spherical symmetry. The magnetic field is cylindrical symmetry, and there was no system of coordinates that will allow you to separate cylindrical coordinates from. So we had to do it numerically. It was not so difficult to do. So we had 180 electron volt, which is interesting. Then we did other things. We did the synchrotron radiation. One electron can produce a gamma ray. We did Bremsstrahlung. One electron goes around in the nucleus, ZA, and it goes out in emitter Bremsstrahlung. So we did all these processes, and we had a lot of fun, and we published an article in Fundamental Cosmic Physics in 1977, detailing all those. Next one. In the meanwhile, the whole atmosphere in the scientific community was about this neutron star business that had been discovered in Cambridge. Now, that is a sad story or not sad story. The point is that Tony Lewis, the astronomer, the radio astronomer who discovered neutron, who died at tender age of 97, 2 years ago, he had a student, Jocelyn Bell, who actually did the discovery, because always the student who did that. She was not included in the Nobel Prize that she got in 1974. So there was a big uproar. Why didn't she? The real discoverer. Because Tony Lewis gave her that as a thesis, but the one who really did the homework, and he was looking at all the strip of paper, looking at all the electrocardiogram coming from the telescope. The one who did the work was actually Jocelyn Bell, and she was not included in the Nobel Prize. And I heard several interviews of her, and she, such a great lady, she never complained, she never said that was fine with her, etc. Which of course it wasn't, but she was kind enough to. So in February of that year, so the beginning of the year, even months after I came to me, in Nature, Tony Lewis and the other people that I told you published this paper in Nature, but they didn't know that there was that sign that was coming from and that's what they call it a little green man, until they would find out that it was actually a neutron star. Now, if it's a neutron star, then you have a simple that is rotating. Now, the Crab Nebula has a period of 33 milliseconds. In other words, imagine Manhattan rotating with a period of 33 milliseconds, 10 kilometers. So, in order for the kinetic energy not to be larger than the potential energy, or the centrifugal force, let me put it this way. In order the centrifugal force not to dominate, you have to have that simple relation. The density, if you have an object that is rotating with the period P, then the density of that object better be larger than that amount, otherwise the whole thing will just blow apart. If you rotate any sphere with the density at that speed, at that rate, with the density lower than, for example, the current nebula must have a density of 10 to the 11 gram per cubic centimeter. The fastest pulsar nowadays is the one that has 0.001 millisecond. The density must be, sorry, not P, rho, but be 10 to the 14. Now, what does 10 to the 14 gram per cubic centimeter mean? It means that 1 cubic
I'm
centimeter,
good. I'm good. I mean,
which is a teaspoon,
I'm good.
weighs
Yes.
10 to the
I'm
14
in
grams.
Minnesota, which is having an 80-degree day while there is still
Gavin,
snow.
could you mute yourself?
It's nice. It's nice. It is nice. People are nice.
So, oh, you can mute it? Okay, we're good to go. Sorry.
Just do the multiplication, and then you get 10 to the 14 grams, the total. So in one teaspoon of neutron star matter weighs like the total weight of humanity, which is an amazing number if you think about it. So that's why the highest mountain in a neutron star is about 10 centimeters because the gravity is so strong, there's no chance, etc., etc. So it's the most unusual, but nature has provided that several, I don't know how many neutron stars nowadays, pulses of 150, 160 that have been discovered. So now it's a common result. But it's amazing to see that you have a density. Now, 10 to the 14 gram per cubic centimeter is the density of a nucleus. So that's why the new rush for the scientists was to find out what was the mass of this neutron star. Is it 2 solar masses, 3 solar masses? So if you have a supernova that explodes, like any decent supernova will do, whatever is left over is whatever is left over. So you ask yourself, will be 1, 2, 3, 5, 10 solar masses? So it was important to determine that the maximum neutron star, the maximum mass that the nuclear force could sustain was, say, a couple of solar masses. So there was a rush to study nuclear physics. We were all prepared for that because we were all ex-nuclear physicists by training. So the next one, this is a pizza slice of a neutron star, 10 kilometers. You can see inside is a liquid, presumably, nobody went there. Neutron, proton, electron, hyperons, sigma and lambda. So the rush was, you nuclear physicists know about nuclear physics, compute the equation of state of this kind of matter and tell us what is the maximum mass that you can possibly sustain. And there was a huge activity in that field, huge activity. Okay, let me show the next one. See, these are the pressure versus density. These are several curves of several people, but nobody came up with more than 2.5 solar masses. So that means that any supernova that leaves behind 3 or 4 neutron star masses is bound to be not a neutron star. So what is it? Well, what is it? Actually, it's our curve is one of them. But there was no big difference. No big difference between the so it was about 2. About 2 well, we had a lot of fun because at one point somebody by the name of Philip Anderson, a Nobel Prize winner at Bell Telephone, said, but if how about the very, very core of the neutron star? Could you go back one step? Is that solid? Are you sure that it's solid? He said that is it solid or liquid? Because we all imagine everything to be liquid. But he said, no, perhaps you're wrong. Perhaps at the very interior, the neutron star is solid. Why did he say that? Because partly because our first director of Giss, Robert Jastrow, became famous in nuclear physics because he invented the hardcore. He said that 2 neutrons or 2 protons, or a neutron or a proton, whatever, they get closer than a certain amount, they repel each other with a barrier that is a delta function. Huge repulsion. So if you imagine to be in the side of a neutron star with the neutrons repel each other so strongly that they feel these walls, they're scared to death, they cannot move. And so presumably they become a solid. They have no chance of going anywhere. So he suggested that idea. There was immediately a rush to show that he was right or he was wrong. As usual in science, you have to factor. And so we decided to go and look at the crystallization. Can I have the next slide, Brad? Next one.
This? One more?
Next one, yeah. Crystallization. This is the most terrible paper I ever written because it's the toughest possible paper I ever written. Now, how you decide between the liquid and the solid? Go ask around to your friend physicists, and they will feel embarrassed because they will not know the answer. We didn't know the answer until one day, by pure accident, we met a guy I didn't meet actually, but my collaborator, Kumar Chitra, met a guy from the Department of Metallurgy, which I didn't know how to spell metallurgy, who said, you physicists don't know what the difference between a solid and a liquid is. He says, no, we don't. We physicists think in terms of wave function. If you take a crystal, you put the neutrons around the edges, and then you compute the energy, and if they stay there, then maybe it's a crystal. But then he said, you have to compute the C44 constant. Never heard of it. So I said, what the hell is the C44? Then he told us the following thing, that the liquid and the solid differ in the following sense, that if you shear a liquid, it will return back to where it was. Or the tendency will be to go there. Okay? But the solid will not. So he said that coefficient C44, which had been invented by I forgot who did that. When that changes sign, if you compute it, and if there is a transition between solid and liquid, that coefficient should change sign. Okay. Born was the man who invented. In 1910 or so, he wrote about 11 papers on the stability of solid and liquid. And one of his computations gave the formula for this C44, which is a very complicated formula. But of course, they usually use it in simple cases. We had to use it in a neutron star, looking for trouble, really. So Kumar Chitra and I decided to do that, and we wrote this paper, which is a very long thing. And lo and behold, what did you get? Yeah, that's it. That's 0.03. You see that the C44 at some density becomes negative. So that was our victory. That the coefficient indeed goes from positive to negative, which was the proof that and at the density of 1.4, 10 to the 15. So it's 10 times the density of a nucleus. But then on the other hand, this is the very center of neutron stars, so it was not surprising. It was not a proof of something that you could use astronomically, but it was a concept, or the proof of a concept, that indeed the interior of a neutron star, if it reaches the density 10 times larger, the nuclear density can really become solid. And C44, I don't wish that computations were worse than my enemy, because it was just terrible. But you need, if you want to do it, you need an Indian postdoc, because Indians are fantastic for this mathematical thing. He knows how to put the neutrons on a cubic phase center, solid, etc. I would have fiddled. So at least we proved that it was. And then we were naive enough to go to NYU to a seminar by somebody whom I will not, his name will not say. And then after the seminar about neutron stars, we talked about it, and he told him that we computed C44. He's a famous solid state physicist. And in the next paper we saw our number being printed. So we were the proud. It happened in the best of families. So our C44 became famous not because of us, but because somebody else saw that it was a good number, and he He didn't say we computed, but he said, but this number. Well, he presented somehow or other. Man. Okay, anyway. You win some and you lose some. So after that, then we also want to see if you want to go to very high density, or you go to cosmic rays. Cosmic rays are God-given laboratory. When two protons, let's say two protons, neutrons cannot do it because they decay, you know. So when you have two protons smacking against each other, by the Lorentz velocity, they actually look at two books because Lorentz contraction. So there are two books smacking against one another and then blasting away again. So people did that exercise of computing the pressure and you can go up 10 to the 17 gram per cubic centimeter. So you can have a lot of fun. But we limited our fun to something that was possibly astronomically viable and not just a curiosity. Okay, next one. Okay, forget about the next one. So, and on the basis of that, I was invited to write a review article for the annual review of astronomy and astrophysics. It's called Equation of State of Ultra High Density, Part 1 and Part 2, and the second one is Part 2. It's the same as Part 1. I mean, but anyway, that was the reason why my work went in there. So then, because of that, I was invited, my whole family was invited to Niels Bohr Institute in Copenhagen, because Copenhagen is the place where you do nuclear physics because of Niels Bohr. They have a huge experience, but they didn't have much experience on neutron star. So they wanted to have somebody who would give lecture on neutron star. They put in the nuclear physics, they put in. So I went there and we had a wonderful year in Copenhagen, and spent a sabbatical, 74, 75. So when I get back, I invited John Archibald Wheler from Princeton to come and give a talk. John Archibald Wheler was famous on his own because in 1937 he and Niels Bohr wrote the first and only and the fundamental paper on nuclear fission, the one that is in nuclear reactor. So it was a world famous scientist. Yes. So he came here, he gave a talk. John Archibald Wheler was a superb human being. Then we retreated to my office, and he asked me what I was doing. I said, well, I was doing this and this and that. And he said, what is the maximum mass of a neutron star? And I said, well, 2, 2.2, 2.3. And then he said, so what happened if what is left behind is 4 or 5? I said, well, I don't know. And he said, then it becomes a black hole. Bang. That was I'll tell you the absolute truth. And I have here his biography that testifies that I'm telling you the truth. Before that, he used acronym like totally collapsed matter. It's very long. Michael, you have to tell your girlfriend to wait. So that was it. Black hole. I was stunned by the beautiful word, simple word. Little did I know, a few years later, his co-author of his biography, by the name of Kenneth Ford, called me up from Princeton and said, I'm helping John Archibald Wheler to write his biography, and I wanted to check with you if you remember that he said the word black hole for the first time. I said, that I cannot tell. I remember that I saw it. For me, it was the first time. But it was first time for him, I don't know, because he was very famous for inventing acronym all over the place. He said, no, we know that because on his way to Princeton, from Penn Station, he's a man who kept his diary. In his diary, he wrote exactly what he wrote here in his diary. He said, the gravitationally completely collapsed object was a terrible thing. He changed that into a black hole. So there is a testimony here that he really wrote it down. He was very happy. It's a short term that caught immediately the imagination. Everybody uses black hole nowadays in politics, in market, and everything, you know. Who mentioned John Archibald Wheler. So that happened on the 5th floor, and at Giss in the 5th floor. That was witnessing history being made. But I didn't realize that there was history being made but then later on I did that. So after that, when I was in Copenhagen, the postdoc had an obligation to give a talk once a month on a subject that was not the subject in which they were working, a totally different paper. Look at the library, find an article that you like, and give us a talk on that. And in Copenhagen, the Niels Bohr Institute is very famous for the cafeteria with the smorgasbord. It's so famous that, I don't know if you saw the play Heisenberg here on Broadway. This is the play where Heisenberg, at the time in which Denmark was under the German occupation, but Heisenberg went to see Niels Bohr, which was the grandfather of everybody, and they went to the cafeteria and they discussed. The problem was that nobody knew what the Germans were doing. Are they building a nuclear bomb or not? Heisenberg was being criticized right and left for not having left Germany until it became under the Hitler regime, and there are many versions of why he didn't. Somebody say he didn't work because they wanted to make sure that science, under his guidance, would limit it to good science. Other people say that that's not true. So he had this big discussion with Niels Bohr, and of course, when you're at the Niels Bohr Institute, the cafeteria, you only use napkins. There's nothing else to write on. And he drew the form of the nuclear reactor that the German was working on a napkin. Then napkins is now in the library of the Los Alamos laboratory because Niels Bohr took it and took it to Los Alamos. And from that, the general feeling was that it was not very advanced what the Germans were doing, if Heisenberg told us the truth. But then the other school that says, no, Heisenberg purposely deceived people saying that this is the nuclear reactor we are doing, while in reality, that's not true. The other part of the story is that Norway was under German occupation, and Germany and Norway had agreed the point of heavy water, which is very, very important. So the reason why the German scientists, many of whom had left and come to the United States, in Italy we also had a very intelligent person called Mussolini, who also invented wanted to imitate Hitler, the idiot, and he also invented the racial law, so all the Jews were. And so Enrico Fermi, in 1937, he would not what Jews do, his wife Laura was. They left Italy, and Italy lost a great deal by losing such a. They went to Stockholm, they got the Nobel Prize, and they came to America, to Columbia here. So I lost a lot of brain power that was lost forever. Anyway, when I gave my talk at Copenhagen I was struck by an article by Dirac. And since when I was a student, I had every student in physics had an enormous admiration for Dirac because he wrote a text in quantum mechanics was the most difficult and the most concise and beautiful text. So I saw him once giving a talk in Turin, but I didn't dare to talk to him. So when I read his article and I understood everything, I said, no, it cannot be. I cannot have understood. There's something wrong, when I said. So when I get back, I wrote to him. He was in Tallahassee, Florida, because after retiring from Cambridge, he was a prominent professor, the chair that Newton had in Cambridge for about 30 years. He retired and he wanted to go to a place where the climate was okay, so Tallahassee, which is not a great university. He went there and he spent the rest of his life there. So I invited him. He accepted, much surprised because he didn't know me. So he came to New York and he started talking about it. Next one, here's a picture of Dirac, is the man in the middle, you can see. Behind him, with not a white hair yet, is me, and some of the other students that we had. The one that we obliterated with a little white is a Swiss astronomer, not intentionally. So Dirac was a man of great humility. After that trip, I'll tell you a little story. He was a great admirer of Tarzan. Tarzan was a Romanian Olympic swimmer, yes. Weiss Müller or something like that. That shot all this picture of Tarzan in Florida. So the Iraq told me to go in the swamp after this. And I got there, I was very scared because you go to a swamp and after a few minutes you don't see where it's north or where it's south because the sun is, you don't. But my surprise, the people there who were renting canoes. She said, "Hi, Professor, how are you?" I said, "Do they know you? Do you go, yeah, I come every once in a while." So you finally decide to have a canoe? And he said, yes. And I said, no, no point in going in that canoe. I said, look at around the swamp, it's full of crocodiles. It's full of crocodiles. And the banks, he said, not a lot, but some. I said, if they sneeze, that's the end of our trip, And Dirac gave me the typical Dirac answer. He said, I have the perfect solution. He didn't say theoretical, but that's what he meant. Said that he had talked to one of his colleagues in the zoology department or so. They told him the crocodile are very sensitive to the temperature. A few degrees temperature different, they will not go there. Or they will go there if it's the other way around. So he says, so long as we keep our temperature gradient within a certain limit, the crocodile will do nothing. And he pulled out a thermometer. I couldn't believe it. I said, Paul, at the time we already calling him Paul, do you realize if this guy sneezes, our canoe, which is already unstable on its own, and with the paddle that I really don't know how to deal with, I mean, this is going to be a major disaster. Well, he kept on measuring the waters. We finally survived and went home that evening, and his wife, an Hungarian wonderful lady, said, Paul, what did you do today with Vittorio? I said, well, we went. She immediately understood. Oh, he said, so you finally had somebody who went with the canoe with you. She said, yeah, naughty boy. That was the reaction. Typical British, naughty boy. Like he. So that was derived with whom I corresponded since 1975 until his death in 1984, and I will tell you something about this. So, what did Dirac do? What was, next one, please? What was the paper? In 1937, his wife told me that during their honeymoon, he came up with this idea. He said, well, that's the story. In 1937, if you take a nitrogen atom and an electron and a proton, you compute the electric force, fine, but there's also a gravitational force. So if you compute the ratio between the electric and gravitational force, 10 to the 40. That's why we don't care about gravitational forces. But the rest said that 10 to the 40 is very suspicious. It cannot be made out of pi or 2 pi or something. It just doesn't make sense. It must be some cosmological reasons. He said, this is not the laws of physics. It's due to the age of the universe. Wow. He said, if G, the gravitational constant, Newton gravitation, was much larger in the past, for example, if it goes like 1/t, and in the past it would have been of the order of the electric forces. Then because of the expansion of the universe, the two forces become separate, and now they exhibit a difference of 10 to the 40. But that's not the laws of physics, that's the fault of the universe is expanding. So he brought in another philosophical concept because the Mach principle, Mach is the Austrian philosopher who always insisted that the local physics is affected at least by the environment. So he said, well, suppose that G goes like T to the -1. That was his 1930, and he published a paper on that. No sooner had he published a paper that Teller, Edward Teller, as you probably know, is the father of the hydrogen bomb. They began director of Livermore. He was a very nasty character. Personal experience, I can tell you that with us. He was also Hungarian, and Dirac's wife was Hungarian. So I remember once I took Dirac and his wife from LaGuardia to their hotel. We sat on his bed, and he said, let's go out. I said, why? Because my wife is going to call her brother, this Wigner, and you know how Hungarians are. They get shouting immediately. I said, okay, let's go out. So Teller had this objection, a very good objection, as a matter of fact. That's why Dirac idea was dead for many years. The idea was very simple. If G was much larger in the past, you take any star that you want. If G was much larger, the nuclear reaction inside must have worked overtime in order to make sure that it would not collapse. And therefore, if they work overtime, that means that they're being exhausted much sooner than they possible. So the sun today should not be the sun, it should be a red giant. So you open the window, you look at the sun, it's not a red giant, Dirac is wrong. End of the story. I mean, that paper made such an impression that nobody touched the idea of the variation. So the first question that Dirac asked me when we give the seminar here, and I remember the call code and had to rent television camera because there were people all over the place to see this monster of Paul Adrian Maurice Dirac. He gave a talk on exactly this topic. Then when we returned to my office, he said, "Would you like to work with me?" And I said, "Can you say it again? Because a guy like you asking a guy like me cannot be, I must have misheard." He said, "No, I need somebody who give a solution to Teller's objection. Otherwise, my theory doesn't go anywhere." And you cannot resist saying no to Dirac. I mean, not only the honor, but the challenge and everything. Anyway, I said, "Yeah, sure. I'll try my best to do something to solve the problem of Teller." Once I solved the problem, I'll tell you how. He sent me to Teller in Livermore. So I said, "Would you please call him and let him know that I'm getting there?" So I took a red eye, I flew in from New York to San Francisco, then we drove up to Livermore. And Teller treated me very badly, very poorly. He used to go around with a cohort of 3 or 4 people that was synchronized. In other words, when he laughed, they laughed. When he smiled, they smiled. It was very unpleasant. So I said, "We'll meet you for lunchtime." I said, "Well, I've been here since 8 o'clock in the morning or something." He said, "But you don't have clearance." And Livermore is make it bomb here, so I cannot have you but at lunch. Okay. At lunch, he said, "Well, I explained the reason why he was right qualitatively, but he was wrong quantitatively. And so he could not kill Dirac. I'll tell you why in a second." He said, "Well, let's meet again at 4 o'clock in the afternoon in the swimming pool." I said, "Again, what am I going to do here for 4 hours in the swimming pool?" Anyway, I had no choice. So we came up in the swimming pool. I brought up my idea, and he didn't believe me, or I don't think he did. And I said, "Professor Teller, there's no way out. I'm going to write this paper. I'm going to send it to physical review, and I'm going to ask that you be the referee. So sooner or later, you're going to stuck with my paper. So, you might as well tell me now." He couldn't tell me now because he didn't have the paper. But that's the only victory there. So I went back and said, "Dirac, thank you very much for sending me to this nasty guy, Really, I was treated very poorly." He said, "Yeah, you know how Hungarian was." "No, I was many Hungarian friends. They're very nice. Teller was just a nasty human being." And Teller was known for very nasty human being. Very, very nasty. He became this, how would I say, let me choose the spokesman for Reagan Star Wars. Because he was the right of even the terrible. It was right to the right to the right. So he was making propaganda to Star Wars, right and left. And then many years later, I invited to the New York Academy of Sciences, which at the time was running. And he accepted without knowing that was the same guy who he mistreated. Or I don't know if you know. Anyway, that evening, we had dinner at our place. And my wife had cooked, misguided, as they can say, a cake that's called a bomb in France. Now, you don't present a bomb to a guy who does bombs, that diplomatically was not. And when all the people around the table said, "Professor Teller, why don't you have this beautiful cake in French, the bomb?" And he said, "No, because of diabetes, there's too much sugar, etc., etc." Then they convinced him to have a slice, after which he said to Laura, "I know something about bomb. This bomb is more dangerous than any one of the ones that That was it. He was a very smart, witty man, an intelligent man, except he's politically oriented to the right, extreme right, was just making an enemy in all Department of Physics. As a matter of fact, one day he was invited here at Columbia to the Department of something, and physicists simply do not go to his seminar. They just, how do they call it? They, it's a little bit late. You want me to begin from start? They exorcised him completely. They didn't want to have anything to do with him because of his past. So he was a very controversial man, and but I remember once he asked me. I said, I'm writing a book on energy. I don't know if he told me that when he was CEO. I forgot. Anyway, and I would like to claim in my book the Benedictine father are responsible for the energy crisis. Oh my God. Here we go, the typical Teller idea. Says, why would you accuse the Benedictine father? I don't know any Benedictine father, but they're a very big person. Because in their logo, it is written ora et labora, pray and work, right? That's their motto in Latin. So he says if they put the same emphasis on work and prayer, that means that work is very important. So they say the Benedict father is responsible for having boosted up work, and therefore they're responsible for the energy. I couldn't say no, so I follow out the idea. You cannot say no to Taylor. I said, okay, I'll follow up with my friend the Vatican and see what. And they wrote a very nice letter back, saying, "Yeah, Professor Taylor, not to me, but he said the idea was very interesting, but the idea that you mistranslated ora et labora means pray, and when you don't pray, just be busy with doing something else. It doesn't mean necessarily work. So you mistranslated them." So that saved me from another embarrassment that I had. Anyway, how did Dirac solve the problem? I didn't solve the problem. Dirac solved the problem, and I just did the algebra. So Dirac said, "What are we going to do?" Well, Teller came up. If you take any book on astrophysics, and if you look at the pages where it said the luminosity of the sun, it will tell you to go with the 8th power of G. So if G goes like 1 over T, of course, in the past, luminosity would have been enormous. And therefore, and the temperature would go like the 5 half of the gravitational constant. So 4 billion years ago, the temperature must have been, if you believe Teller, must have been 500 degrees, which is higher than the boiling point of water. But there is evidence that water existed on Earth 3.8 billion years ago. So Dirac cannot be right. The Earth wasn't boiling. So Dirac was really up the creek without the paddle with this kind of thing. So he needed somebody. But he came up as usual with this brilliant idea, brilliant as he was. He simply invented the following in elegant suggestion. He said, okay, instead of one time, let's suppose we have 2 times. Schrödinger equation, Klein-Gordon equation, Dirac equation, all the equations that we do in atomic physics, they define their own time, which is the atomic time. Certainly true. So long as the theory equation contains a mass, then mass will give you a unit of time. So the atomic time is the most natural thing. Now let's take Newton equation on the other side to the Einstein equation. They also define their own time, which is called the gravitational time. Yeah, the gravitational time. So he asked himself, here we have atomic physics, here we have gravitational physics. Both of them as 2 branches, they define their own clock. Are the 2 clocks the same? In the gravitational units, and now, if I want the moon, if I have the moon and I want to make measurements, for me, the gravitational constant is constant, and because it's the string of the clock. But in the atomic unit, it doesn't have to be. In the atomic unit, it can vary. Now, we never use gravitational clock because you don't use the moon to use atomic clock. The atomic clock had been in existence in 1955. For 2,000 or 10,000 years, people use gravitational clock, right? The moon and the sun and the air. So don't mix the 2 units, Dirac said. Let's explore what is the difference between the 2 units. Next one. Oh, sorry. There is a principle in in physics that is called the strong equivalence principle. The strong equivalence principle doesn't mean that it's very strong. It means that what is demanding is very strong. Namely, that the two clocks are the same. That's an enormous simplification. Everybody accepted it, but there was no proof of it. So, in a sense, one postdoc from Israel, we wrote two papers, astrophysical consequence of violation of the equivalence. In other words, suppose the two clocks are different, then what would happen? Next one, let me see. Here is the story. We work with Dirac instead of computing all sorts of stuff from the Big Bang down. Every process we redid it using the two times theory, and nothing wrong about it. So we prove, and that's an important concept, we proved that the idea was compatible with the data, not necessarily required by the data. That's a very different story. So the fact it's compatible doesn't mean it is required. So we needed somebody to do the experiment. This somebody was the people at Livermore who do this for a living. They knew exactly what Dirac was doing, but they said until we have a proof that you can show to us that it's completely compatible with anything we already know, we will not do the experiment. It is a numerical experiment, very complicated. So it's a fair request. So once we finished that, we said, okay, let's go and look at the data. The data were actually Viking data. There are two Viking in 1976. One is orbiting Mars, and the other one is landing on Mars. The one landing on Mars was useless for our purposes because the topography is too complicated. So we wanted to use the one that is orbiting Mars. And many laboratories of physics on the Earth have been using it by sending it electromagnetic wave and computing the time that it takes to go there and come back. If there is a variation of the gravitational clock measured in atomic clock, and if Mars is doing any funny business, you should measure it. It should come up in your measurement. So with the ideal clock. But then can have the next one before the. But then the news came that the Reagan administration wanted to kill the Viking for economic reasons. So I told the Reagan, no, don't do that. Don't do that, please. So you have to write to everybody in Washington and tell them not to do it. And he said, nobody knows me. I said, yeah, you don't know them, but they know you. So I wrote this letter for him, which he signed. And we sent it to Keyword, which was the science advisor of Reagan, a plasma physicist from Los Alamos, who certainly knew who Dirac was. And in this letter, Dirac explained why we should not turn it off. And if you go back one, that's the answer of a Keyword. It says, "Dear, thank you very much for letting about the Viking Lander. I agree with you. Then discontinuing this variable experiment will not be a wise decision, and I was pleased to find out that NASA has in fact made plans to ensure this continuous operation." And that was immediately. We didn't have an email at that time, So the fact it came right back, it means they must have hit it. And the letter was sent to. Can you go back one? We sent the same letter to Press, who was the president of the National Academy of Sciences. We sent it to Washington to the big boss at NASA headquarters, and they immediately said, "Oh, you're right. You shouldn't discontinue." It was costing nothing, so for them it was not. So they started in 1976, but since they measured the time with that precision, we needed more years, to make them. So we succeeded in having these people discontinue the program of turning. And so when I get this letter from, Dirac letter of May 11, and the reply from the White House of May 27. It took them 2 weeks to reply. I said, yeah, thank you very much. So it does show that you want to put a little bit of pressure. It works. So next one. Okay. So here is this. We simply said that the Einstein time or gravitational time and the atomic time were not unit like this strong equivalence principle, but they were could be scaled by a function beta. Nobody knew what beta was, or neither did we, but we showed that even though we didn't know that the power law that we simply gave very good results. So next one I think is, so with that 2 times much of the pleasure of Dirac, we solved the problem, because then it turns out that it's true that luminosity goes up, but not to the 8th power, to the 5th power. And the temperature goes up only with linear energy. So those 2 numbers are perfectly compatible with the no boiling water, nothing of this. So it was not the idea that Taylor had, but it was quantitative. He just used the wrong equation. And when I went to Livermore, I was trying to explain to him what did he do wrong. And he didn't accept it, neither at lunchtime, neither in the afternoon. We must have accepted it as a referee, if he was the referee, I'm not sure. But anyway, so the objection has finally been resolved. And then came the variation that the theory predicts is that the variation is 5 times 10 to the minus 11, which is the age of the universe. So we engaged the people from Livermore. They had this huge, gigantic numerical code of all the planets. They put in, every planet has determined the mass, the distance. They determine everything. As long as you put in more data, they can come up even the political affiliation of your party. It's incredible. But it's a time consuming. They didn't want to do it unless they had to. Now they couldn't resist anymore. They had to do it. And the result was the one you read below. The data was 0.2 to 0.4, 10 to minus 11. So the Dirac prediction was 5, it was 0.2. Bad news, really bad news. So can you show the next one? This is the paper that we published in Physical Review Letters, in which it says, I cannot read it, but it says, oh, here it is. Experimental test of the variability of G using Viking Lander ranging data. The first people in the first 1, 2, 3, 4, 5 people in the row are the people at Livermore, and downstairs it's myself, my portfolio. So the idea of Dirac was wonderful, but it didn't work. So it took up to me to go to Tallahassee and tell the old man that the data was not right. That was it. It was a tough trip, frankly. So so he simply said that the idea was too beautiful to be false, because Dirac had always beauty as one of the guiding principles. And if a question looked ugly, he said they must be wrong. It cannot be right. A beautiful equation is probably right. So he said that principle all the way to the end. He said, but he couldn't prove otherwise. He said we have to stand to the experimental data. If we are off by an order of magnitude, then there's either we miss out some planet, which is possible. We had a lot of problems, for example, with the asteroidal belt around Mars. We can create a lot of epochs for which we didn't have a very good model. But that's the way it stands. And that was the best. That was 1983. Dirac died in 1984, October 20th. It was a Friday morning. The day before, it was a Thursday, he called me up to thank me for a suggestion that I did. It was a very serious suggestion. He was a great admirer of Piotr Kapitsa. Piotr Kapitsa, I'll tell you later. Piotr Kapitsa is a famous Russian scientist, Michael can attest to that, who was very friendly with Dirac when they were together in Cambridge in the 20s. And there was a volume being written in honor of Kapitsa, and Dirac had promised a chapter, and he was late in writing the chapter. So when he called me, he said, I'm very concerned, I cannot finish writing. And I said, Paul, there is a simple way. Since you have everything in your mind so clearly, go to your secretary, don't bother writing it down. There's no email at that time. just tell your secretary the text. She will type it and fax it to Cambridge, and you've done it in half an hour. Great revelation. So next morning, Thursday, October 19, he called me up and thanked me for that simple suggestion that made him very happy, because Kapitsa was one of the great heroes. And the day before, Friday, October 20, his wife called me and said that he had passed away on his sleep. So he had died in October 20, 1984. It's written there. The day before, he had commented that while accepting the Viking data, he considered two things that were too beautiful to be wrong. Then I went back to look at the Chandrasekhar, another Nobel Prize, and that says that the simple is the seed of the truth. And Dirac lived all his life doing simple things. And precisely because it was simple, he invented antimatter. I mean, and one of this amazing. But let me tell you about Kapitsa was why. I remember that we had a dinner with Dirac and C.N. Yang of Colombia, who was also Nobel Prize for the violation of parity in interaction. And the news came that Sakharov, Andrei Sakharov, you certainly know who he was, had received the Nobel Prize for peace. So everybody was very happy except Dirac. I didn't say anything, but I know him as well as I did. I realized that he was not happy with the idea. But I didn't dare to ask because. But somebody else did, I forgot. And he said, very forcefully, he said, how could you give I'm citing it verbatim, how could you give a Nobel Prize to a man who created the hydrogen bomb? Bang. Oops. Sakharov was indeed in charge of the hydrogen bomb. The 50 megaton hydrogen bomb that the Russian exploded in an island in the Pacific, destroying the whole island of Pacific. So how could you give the Nobel Prize for peace to a man? And of course, it was absolute silence. Nobody would. But then we started saying, why you have such a. And then he said the Nobel Prize for peace should be going to Kapitsa, and there's not been given to him. He said, why? And he gave a very short answer. He said, because he said no to Stalin. Dirac was like that. He would give you an answer that was nailed to the wall. Now, saying no to Stalin was not a very hygienic thing to do. I mean, the next morning you can find yourself in Siberia or some other resort places, you know. But when he left Cavendish laboratory, where he learned cryogenics, he went back to Moscow, and Stalin asked him to become head of the atomic project that would create the atomic bomb. He said no, he will not do it. Kapitsa will. Well, he showed guts. And Stalin didn't do anything. He let him become director of several institutes, etc. But then Greg also told us that they met in Germany the summer before, and then Kapitsa told him the following story, which I want to tell you because it's an amazing story. He said that you don't remember because you were not alive yet, but in March 1953, Stalin died. Then Laurenti Beria, who was in charge of the atomic project, Laurenti Beria was head of the security and the secret. At that time was not the KGB, it's a different name. Could not stand Kapitsa because Kapitsa was keep on writing letters to Stalin saying, watch out because Laurenti Beria is a bad character. But that letter never got to Stalin, it was stopped at Laurenti Beria. So when Stalin died, Kapitsa told Dirac always that he was afraid of his own life, that finally Laurenti Beria had his vengeance against him. So one day he was in his dacha, and he there and two people knocked at the door, and then clearly military people. He said, we have to look through your apartment, or whatever it's called, a library. And Kapitsa said, that's it. That's the end of my day. They will put some piece of paper in some books. They will find it, and they will accuse me of working against the regime. The usual trick that, and that's the end of my life. But then it became very suspicious to Kapitsa because these people would not leave. They would keep on hanging around the apartment. So it would become very suspicious. Then noon came, and at noon these two people said, thank you very much, Professor Kapitsa. We have found or not found, or whatever they said, what we were looking for, and have a good day. At which point Kapitsa said, there's something very weird here. He turned on the radio, and it turns out that at noon, Laurenti Beria has been arrested. So the interpretation that Kapitsa gave is that actually those people were not there to do him, but to protect him. Said these are the people that Stalin foresaw that they could be coming against Kapitsa, so he wanted to have some people in case Stalin died, that Laurenti Beria would not have revenge on him, and they were there to protect him. And that's exactly what happened. Kapitsa got the Nobel Prize in 1974, if I'm not right. He died. He has an important, super important role in the physics of science. He invented the whole school of cryogenics. And in 1968, coincidentally, the year he came to Giss, he discovered superfluidity, which is the equivalent of superconductivity, which had been discovered many years before. So he's a man of great power, and he left a school of scientists of first class. And that's why Dirac was so afraid that he wouldn't be able to write this paper for his friend Kapitsa. So that's why he accepted my suggestion to simply tell the librarian or the secretary to simply. Now, I've been talking for how long?
We have like 40 more minutes.
Okay, 40 more minutes. Okay. My last sinful thing is turbulence, which I will never be able to part from it. In 1974, Heisenberg, the great old man of science, Germany came to United States to visit. The first place was Colombia. He gave a beautiful talk at Colombia, and I was there like thousands of other people. And in the list of the real German professor, with double-breasted suit and a golden chain and a really classy character. And he among the problems that he considered to be unsolved in physics, they needed solving. The third one was turbulence. And I was very surprised. I didn't know anything about turbulence. I had no idea. So I waited to talk to him. I waited a long line to shake his hand. And by the time I got to him, I said, you quoted this turbulence, but could you give us some references that I would like to learn something about it? So, and I remember what he said. He said, "Are you a physicist?" I said, "Well, I'm trying to," because he said turbulence has been in the wrong hands. It's been in the hand of mathematicians who can only study exact problems, and there are very few of them, or engineers who actually want to describe it, not necessarily understand it. So we need a physicist really, because that's a physics problem. So I said, fine, can you send me? He said, yeah, you can begin reading my doctoral thesis. Now, since the man who invented the uncertainty principle, one of the founders of quantum mechanics, I thought that he was pulling my legs. I said, no, what has it got to do with turbulence? So I went back to Dirac and I said, you great hero, Heisenberg, pulled my legs and asked me to read his thesis. He said, no, his thesis wasn't fluid dynamics. What? Typical what? So yes, he was a student of Sommerfeld, one of the toughest scientists in Germany. And actually his thesis was on Poisson flow or channel flow, but it was a problem of hydrodynamics. And he is the man, by the way, here. So I got to the library. The library was kind enough to take that thesis from the headquarters, had been translated into German, which I don't speak, so I could read it. It was 200 pages of algebra. At the time, there was no computer. So Heisenberg solved the problem that had been a riddle for many years in the time of Rayleigh in 1880. They could not understand what was going on in channel flow. He invented in that paper the concept of turbulent viscosity, which everybody uses in 2023. We still use the concept of turbulent viscosity, which Heisenberg invented in that paper. So I started working on that paper. I read that paper. Of course, I had no idea what to do, but I realized the following thing: that first of all, turbulence is ubiquitous. We are born and live and die in the planetary boundary layer, which is turbulence. The backstage part is here. Each egg is the backstage from planet. All the stars, sooner or later, become turbulent. The oceans are turbulent. So it's not an exception, it's the rule. So why is nature using turbulence rather than something else? Simply because turbulence is the most efficient, effective way of transporting stuff. It's much better than radiative transfer. So much so that if you take the sun, 10 to the 10 centimeter, the last 30% of the sun transport heat through convection, because nature finds it more convenient, more efficient to transport it through convection. So, but there is a drawback. The turbulence is, in a nutshell, a manifestation of a nonlinearity. And nonlinearity is the toughest cookie you can possibly have. There is no theory for nonlinearity. That's a problem. So you up the creek without a paddle. You want to study a process whose underlying physics is nonlinearity, but you have no theory to assume. Any person will say, "Okay, I'll give up. I mean, it's a loser." Now, in 1953, a German scientist, Erika Bonvitense, the second name is her husband. She moved from Germany to University of Washington. In 1953, she wrote a paper called The Mixing Length Theory in Stars. That paper has been cited a gazillion times, literally. So since that moment, everybody's been using the mixing length theory. What the hell is that? Well, if you take a turbulent system characterized by a Reynolds number, the size, the nonlinearity, if you take a linear system, the kinetic energy grows up exponentially. There's no stopping, which is non-physical. If you put nonlinearity, then the energy becomes constant, stationary, because the nonlinearity distributes the energy to everybody, rich and poor. So that's what the eddies are, manifestation of those. In 1925, Prandtl, famous German scientist, invented the mixing length theory. He said, that's true, there is a lot of eddies. But since in engineering flows, the viscosity is not that low, it's rather big, all this huge amount of eddies can be represented by one eddy. So he called that the mixing length theory, which made sense in an engineering high viscosity environment, certainly not in stars. Bonvitense adopted that idea, applied to the sun, and it has been. I never liked the mixing length theory, I must confess. And in 1992, with a colleague of mine, I wrote a paper in which I took all the eddies rather than one. And my colleague Dick Stoddard, whom we miss deeply, called that the FTS, the full turbulence eddies. Well, that paper which I wrote has been cited, I checked this morning, has been cited 951 times. Because from 1953 to 1992, nobody thought about extending the one eddy, which was clearly an approximation, all the way to the other eddy, which it was possible. Not an exact theory, but it was better than that. Now, when the then director, Jim Hansen, when he was director, he would keep on telling me, well, when are you going to apply this model to the atmosphere and when you apply to the ocean? It put some pressure on me, and rightly so. So in 2018, I delayed that because I didn't know how to do it. So in 2018, 2019, we published two papers on the Journal of Physical Oceanography, of which I think I brought some. Oh, keep on going. I'm going with a decay that I cannot have the time to do it. Keep on going. Okay, here it is. Ocean atmosphere starts at turbulence. Why? Because there's a very efficient transport mechanism. Nonlinearity is the heart. Okay, let's go. The next one, please. Without modeling nonlinearity, only heuristic model with no predictive power are possible. So Okay, next one. In 2018, we published, in 2019, we published with Michael and Li Chang, we published a paper in which we did our best to produce a model for convection, for turbulence in the ocean. And here is one result. The full curve is, this is the kinetic energy, centimeters square per second of these edges. As you can see, it reproduces the dashed line is the topic Poseidon data. The dotted line is the numerical simulation data. And our, which is an analytic formula, it does as well, if not better than the other. This was one first example. Next example. Then we computed the global average temperature, as you can see on the left. And we compared it with many other people, they're all cited there. DFBL, KIL, NPI. So our KIL is the dotted line. As you can see, the global average temperature in time remained constant because many of this GCM computation, they give the energy, the temperature goes down, etc. Our was very stable without fudging, without doing any particular. The global average salinity is even better. It's very flat. I think that the two curves that fall down, which is clearly unphysical, have been corrected now, but not at that time. Next one. This is the Atlantic overturning function, which is well known, and the result compared with the figure 23 of a review article. We're doing very well there too. We compare with about 7 of different GCM. Next one. That is the heat transfer, the poleward heat transfer. It goes from minus 80 degrees to plus 80 degrees. These are the data. The NCAR is the full line. GFDL, all the other hours is the dotted line that would fall right in the middle. So our model works as well. With the other, without having this falling off the forward heat transport. And okay, next one. I think. Oh yeah, in the Drake passage, is between Argentina and there have been a lot of measurements. The observations are there. The number Schwerdrup. And Schwerdrup is 10 to the 6 meter cube per second. The passage through the Drake passage, observation is about between 120 140 Schwerdrup. But you see, the purple one is 20, so it doesn't work. The green one is not. Oh, the one on top is too large, and the ours is the one that dotted line. So I think we did pretty well on that one. I think that's the last one, right?
Yeah.
So let me conclude by thanking you the physical resistance of having listened to all the stories. I thought if you did not learn anything, at least you were amused a couple of times. And if you don't get amused when doing physics, then, as Dirac told me once, then give up and do physics. You have to be happy in what you're doing, and I'm happy that I'm still doing something that is not exactly trivial, even though it's becoming more and more so. I thank you very much, all of you.
Thank you so
I'll
much.
be unhappy to answer any question.
Yeah, we have the room for another 25 minutes.
Okay,
so
I have full time to make myself a fool of myself.
yeah, we can.
No, I welcome any kind of question in my time. That's what we're here for.
Yeah.
Science is question and answer.
Yes.
Remember what Bohr once said. There are no. How did he say? There are no silly questions, but only boring answers. So I think that is very true. It's so yeah. Okay. Any question? I'm glad to field them. So life can be fun. Yes.
So you talk to us about your years after coming here in New York. You talked about your arrival in New York.
Yeah.
So how did you grow up? How did you decide to study physics? And how was your...
Well, that was an easy decision. When I was in the highway and high school, I liked chemistry because in Italy, at least, they teach chemistry before they teach physics. And I love chemistry. But then I realized that one day I wanted to do an experiment at home with sulfuric acid. So I created sulfuric acid, which turned out to be a gas, but I wanted to have a liquid. So little did I know that in order to go from a gas to a liquid, you have to put lower temperature and high pressure. I can only lower the temperature, but not the pressure. And then I put the whole thing under the sink and it exploded. So I saved my life by sheer miracle. At which point, my parent had a strong rule that I would not do any more experiment, at which point I found that chemistry was dangerous to my health, was very smelly, and so the year after that we studied physics, and so I fell in love with it. So I never had any problem from the year after that I would become a physicist, bad or good or mediocre or whatever. So I liked physics from the very beginning, but the physics they were doing in my university in Turin was not good for me. I mean, in 1956, Eisenhower had a famous meeting in Geneva, Atom for Peace, in order to blunt the feeling that the world had that America had exploded 2 atomic bombs in Hiroshima and Nagasaki. So you put Atom for Peace, then it gives a completely different. Out of the Atom for Peace conference came CERN, the European Center for Nuclear Research. And since Turing is next door to France and next door to Switzerland, there was such a magnet that everybody was going to study at CERN. And I was sent to, being a decent student, I was also sent to CERN in Switzerland to study the field they were doing. I didn't like it. I didn't like forget about the Swiss. I didn't like the field they were doing, so I came back to my director of thesis. I said, I don't like this proton-proton interaction. I didn't know what I wanted to do, but I didn't know very well what I didn't want to do. And that's what I didn't want to do. It just appealed to me. So my director was a Russian guy from Minsk, from Belarus, who was a refugee from Russia. Also, he understood exactly. He said, well, I understand. I can send you out Europe for a couple of years, but we cannot find it unless you find it yourself. And I said, yeah, but I don't know what I'm looking for. Only. So I said, well, I have a Russian friend of mine who's also at the University of Mexico. He's also Russian, who's building up a group of nuclear physicists. Would you be interested in going there for a couple of years? I said, yes, of course. So I spoke Spanish already, so I went there and I was received very cordially. And so I started off with something that was a continuation of what I was doing with nuclear physics. In particular, we were working on if you ever heard of the mass formula. The mass formula is a formula analytic that gives you the binding energy of any atom. And that is very useful for people who do nuclear explosion, because they have so many different atoms, they need that formula. So I wanted to know whether that formula could be derived from the shell model, which was the rate. So I worked with that for several years but then I was getting all this paper from Giss, from only two, on the neutrino energy losses from supernova, etc., etc. So I couldn't wait meeting him, and when I met him, then that turned my life around, because he then invited me to Giss, and that's what my life changed from there to here, and it started a brand new. But the training on nuclear physics was very useful later on when we studied neutron stars. As a matter of fact, it was invaluable for me to have that experience. Otherwise, I would not have been able to do anything on nuclear physics. So that was a very valuable experience. But of course, it was a completely different planet. Beyond, as I told you, 1968 was a revolutionary year in science and in politics. That you're being caught in
But what was your PhD thesis on? I mean,
solid state physics. It was on solid state physics. It was a group theory, so it was. They gave it to me, which I hated all the time. I didn't feel that how to do group theory, apply it to solid state without having to do all the computation. Just the symmetry property. If you use SU3 or any other rotational groups, how many properties of solid can you derive just by symmetry rather than doing some computation? So I must have derived some result which is semi-relevant because they said that's okay. But I was not close to my art. I wanted to do something that had to do with, broadly speaking, with statistical mechanics, but it was not really. I even went to Utrecht for 1 year, no, less than 1 year, when I realized that A, could speak the Dutch, B, they would never learn Dutch, and C, that no people that spoke Dutch because they spoke English all the time. I said, no, it was raining all the time. It was very nice people. The Dutch people are the nicest people in the world, but it was raining every day, and I said, no. So I went back, and they told me, why don't you go to Bexel, which has a different weather than Utrecht. So I went there, and I was very happy there, and I started off my new life there, doing nuclear physics, but actually we were working on, there was this famous Soviet scientist, Spartak Belyaev. Spartak Belyaev, who spent a year in Copenhagen, and he wrote a famous paper on superfluidity in nuclei. And so I loved that paper, and I grabbed that paper, and I studied it, and that's what I want to do, superfluidity, invented by Capisa, precisely, to nuclei. And that was the chapter in physics that was then become very modern. So I published something relevant or irrelevant on superfluidity of nuclei, and computed the binding energy, etc. So it took a while to get into the right groove, but when you got into an atmosphere like, because at that time Giss was very different. At the time we had a lot of people coming in as advisors. They used to come in just once a month, once every 2 weeks, like that, and they would just go around and talk to people. Ed Spiegel, for example, was my roommate. One day I found him there, and he was chit-chatting to people. Then we had Ben Strongman, one of the most famous astronomers from Princeton, was coming by and talking, because we had a lot of astrophysics. Actually, we had 17 postdocs at my time practically all in astrophysics. So there was very different atmosphere, and of course, until the President Reagan decided to cut down the NASA budget in '68, severe cuts. Well, at that time, if I remember correctly, NASA budget was $9 billion of that year, and he cut it almost in half or something. So survival was the name of the game. And Jastrow, the then director, had the wisdom to try to change the astrophysical aspect into the more Earth's applied kind of science, and that's why we started going into weather prediction and then changing to. So there was a big transition. Many people left, said that they wanted to do what they've always been doing, and they were not pleasant. I went to Pittsburgh to look for a job, and they offered me a tenure position at Pittsburgh University, but my wife said no. That basically was the reason why I said no. So I was stuck it around and showed, but certainly Jastrow showed a lot of foresight in changing the institute for any astronaut advisor from MIT, for Charney. Charney was here being advised on build up. So the fact that you have computer doesn't mean that you can do good physics. I mean, sometimes you need more than just computers. And so there was a couple of moves that Jastrow did was really saved the institute from collapsing, basically. So the greatest loss was actually at Hazard headquarters, with all the managers they'd accepted to be managers there with the reduced salary from what they have in the industry. But they did it because of the beauty of the project, going to the moon. It was more enticing than making a big salad. So they offered the expertise, the managerial expertise, but when, and was very successful, as you know. But when the wind changed and those people left, so that was, I think, was a great loss from NASA, but the institution survived, as you can see, and here we are, 50 some years later. Does that answer your question? Thanks.
So basically, all your studies were in Torino?
Yeah.
Up to your PhD?
Oh, what?
All your studies up to the PhD
Yeah.
were...
Yeah, I was born there, you must have learned the name of Avogadro in your life, in chemistry. Well, I was born in Turin. That was great glory. Turin is a funny city, It's Fiat, if you want. The T in Fiat means it's from Torino. Fabbrica Italiana Automobili Torino. So, in the city of Fiat, Olivetti was there. And except it was a very famous city. Royals, all the kings of Italy come from Italy. I don't know if that's good or bad, but all the kings of Italy. So then when I was born, I given the name of the king, of course, because that was standard procedure. So,
Juventus.
eh?
Juventus.
So it's a city that is, the Shroud of Turin is also in Turin, but it's too close for comfort to CERN, CERN is such a good magnet that developing other branches of physics, at that time at least, developing other branches of other than the one they're doing at CERN was not an easy task, and I was the first victim of that I couldn't. Well, I also didn't know exactly what I wanted at the time. But Turin was the city where Avogadro was born and raised and invented the Avogadro number. By the way, I don't know if you know it, but you might be interested in knowing that the number of stars in the universe is the same as the Avogadro number. Just I'll pass you on the information. 10 to the 23 stars. So you remember one number, but you catch two. I mean, 10 to 23 plus or minus a factor of 10. But Turing was very famous for the classical studies, especially in mathematics, especially differential equation, was the king of our study. I mean, we had to learn all the possible hypergeometric functions you can think of, which support the Laplace transform. Nowadays, students don't do it because they go to Google, they find everything there. But at the time, we had really to learn all the differential. Italy was very strong in last century on differential equation, Ricci equation, Riccati equation. They were all severe equations. It was a big school of people inventing and solving differential equations. So it was a tradition. And the professor that we had was also famous for having invented an equation that is fundamental in the hydrodynamics of the wings of a plane, the trichomy equation. So there was a strong tradition in mathematics. We were about 3 years in a row studying all this.
Where was Bernoulli from?
Where
was Bernoulli from?
Switzerland. Yeah.
Italian Swiss. Italian Swiss.
I don't know. I don't think so. I think it was a French Swiss. I don't know. We have to check. The two brothers. Italian. Yes, it sounds. Yeah, the two brothers, right? Jacob and Bernoulli. But I think they're originally Swiss. But no, they were not Italian. So they were not born in Italy. But that was 1870 or so. Yeah. Yeah, no, Bernoulli definitely was. Definitely. No, the greatest glory of Italy, of course, it was Marconi, obviously. Marconi, Majorana. Marconi, I'll tell you a funny story. Sense of humor of Italian mothers. Marconi died one day, the same day that I was born, and there was the head of the newspaper said, Marconi died today, and my mother wrote in pencil on the bottle says, "Disaster never happened alone." She knew something I didn't know. So Marconi is one, of course. Galileo, of course. Fermi. Majorana. Well, Majorana is still unknown. Majorana was considered to be at the same level of Newton, etc. But of course, he disappeared from the face of the earth when he was very young. So nobody knows. The Majorana case is still an open case. But he invented a neutrinos, and even today they dispute whether the neutrinos is a Majorana neutrino or Fermi neutrino. There was a man who at the tender age of 23, 24, was given a chair because of the beauty of his brilliance and his performance. And then, unfortunately, he disappeared from the face of the earth, and nobody knows. Nobody knows whether he. There's all sorts of theories of Ettore Majorana. But this is the school in which Fermi, of course, is the one that lasted. It had the greatest impact on time, because in December 2nd, 1942, Enrico Fermi had the first nuclear reactor in Chicago being stable, not exploding, but being, what they say, not stable, it's another word. Anyway, under control. He was creating energy. Because it's easy to have a nuclear reactor. If you let him explode, there's no problem. But if you want to confine it, you have too many girlfriends, Michael, in my opinion.
He started in Schermerhorn. His first lab was at the basement of Schermerhorn.
Who was that?
Fermi.
Oh, yeah, of course. Yeah, he left Rome because of Mussolini. He went to pick up his Nobel Prize in Stockholm. He came here, and Rabbi invited him to Colombia. Yes. And then from Colombia, he went to Chicago. And that's where he spent all his life. And Los Alamos, too.
They didn't want to have an explosion in the middle of Manhattan.
No, but in Chicago, nothing exploded. I mean, it was a very successful. It was a funny story, because he was a very careful man. He knew there was working with radiation and extra radiation all the time. And he was always telling his students, be careful, etc. And then he died at the age of 57 or 58 because of radiation. He contracted leukemia, whatever it was. So it was a tragic loss, but when he was 17 or 18, the year that he went to university, he went to the normal school in Pisa, and he wrote his first paper in there, in which he solved the Laplace equation of a vibrating chord by solving those equations in a way that now you can find in any book with all sorts of Laplace transform, etc. At the tender age of 17, he solved those equations. He just was an amazing character he always called himself not a quantum mechanic, but quantum engineer, because he didn't like the quantum mechanics in the grand old scheme of Heisenberg or Bohr. He liked applied quantum mechanics. That's why he was really a man of laboratories, etc. And that's also, when he was born in 1905 or 6, there was a meeting in Washington at the centenary of his birth, and some of his friends who were with him at Los Alamos, they were still alive, simply because people said, how can the Fermi get into quantum mechanics so late in his life, comparatively? He said, because the first contact with quantum mechanics was with Heisenberg. It had the matrix formulation, which did not appeal to Fermi. But then, when Schrödinger invented this equation, that was a differential equation. So then Fermi was able to put his teeth onto the differential equation and solve it. By the way, about Schrödinger, once I had the pleasure of inviting his daughter to dinner in Halbach. She's a small village in Austria where he's buried. So I went to the cemetery and looked for the grave of Schrödinger. It's just the name, that's all. There's no. So, but they told me that his daughter, his daughter was retiring, living in Albach. They give me the number, so I called her up. I said, and she came for dinner, and he told me not a story about his father. It was an impossible character, very difficult character. He wouldn't listen to anybody, stubborn, and then
All physicists are.
yeah,
All physicists are.
yeah, physician. But anyway, she told me the story that the last time that he visited her, she was a biologist of a certain renown. She was professor in Cambridge for many years. Then she retired too, and then the last time I saw, he said that he had showed some kind of pneumonia, wasn't feeling well, so he kept on recommending him to take care of himself, etc. But stubborn as he was, he didn't listen to her, and that did him in, you know. And but Schrödinger was certainly a person of great. I don't know if you ever read, but if you haven't, I suggest you do. You know, when Hitler in how the hell what is the verb in Austria conquered Africa, the Enschloss in 1938, many physicists from Austria left, and Schrödinger was certainly the one that went to leave. So the president of Ireland, Eamon de Valera, invented the Institute for Advanced Study in Dublin, and it was for Schrödinger, who wrote there a book, and it was called What is Life? It's no more than 50, 60 pages. You should read it because it explains life not from a biological point of view, which he was not, but from the physical point of view. Why is life contradicting the law that says that entropy always increases? Why doesn't it increase? So it invented the concept of negative entropy. It's a beautiful little book which you can find any I think it's called What is Life, but Schrödinger and Life you can find. And that was one of his most beautiful. Because the rest of Schrödinger equations had been taught in school, so you learn it. Yeah? But that book on life was very illuminating, and for biologists too. I mean, it's not only for physicists. You know? He put the physics and biology together in a very charming, unique way in my life. I haven't written a book because it's such a short, small book that was really amazing. He had it all in his mind. Irving Schrödinger, yes, sir.
So we're just about at 3 p.m. So unless there's any remaining burning questions, I think we can just give Vittorio another round of applause.
Thank you so much. Thank you.
Yeah, I think we can just close there. Thank
Yes.
you everyone so much for coming. This was so cool.
You said there's food somewhere?
Yes.
Yeah.
There's probably leftover food out in the kitchen, just around the corner.
We list the food.
Yes, it looked really good.
It is very good.
So these you don't.
It's okay. It's
All good.
okay. Thank you.